Hello guys, here we have USAPHO-2016 question number B2. So in this problem, I will mainly emphasize on part C because part A and B are very conventional and appear very commonly in exams. So let's begin. In a spherical region of space of radius r has a uniform charge density and total charge of plus q. An electron of charge minus e is free to move inside or outside the sphere under the influence of the charge density alone. For this part, ignore radiation effects. Consider a circular orbit for the electron where r is less than r. Determine the period of orbit t in terms of the quantities. And similarly, in the second case, we have to assume r greater than r and again find the period of orbit. So first let's work on these two parts. So this is the approximate diagram, and here the charge density rho in the region will come out to be 3q over 4 pi r cube. So in part A, for the first part, what we get is that the electric field at a distance r will be equals to rho r by 3 epsilon naught, and the electric field will be providing the necessary centripetal force. So E times rho r by 3 epsilon naught equals to mv square over r. So from here we can get the velocity, and again the time period can be found trivially, and the time period will come out to be 2 pi root of 4 pi epsilon naught m r cube over eq. So this will come out to be the time period in the first case. Notice that this is a constant for all small r because it is a simple harmonic motion, and so the time period will be constant for each radius r. And for second part, similarly, we can get that electric field will be kq over r square, and again by the similar manipulations we can get the time period to be 2 pi root of 4 pi epsilon naught m r cube over eq. Notice that here it depends on r because it is not a simple harmonic field. Now for the third part, assume that the electron starts at rest at r equals to 2r and determine the speed of the electron when it passes through the center in terms of the given quantities. So here first we will find the potential difference between the 2 points, and we can apply the work energy theorem after that. So this is also very trivial and straightforward. So first of all, the potential difference is equals to minus integral E dot dr from 2r to 0. Now if you integrate it, you can divide it into two parts as from 2r to r integral of q by 4 pi epsilon naught r squared dr plus integral from r to 0 q by 4 pi epsilon naught r over capital R cube dr. And when you integrate this, in the end you will get the potential difference to be q by 4 pi epsilon naught r. So from here, in the end, the velocity you get is root of 2eq over 4 pi epsilon naught mr. Note that these are very straightforward parts, so I am not showing all the calculations. You can work them out yourselves. For the B part, accelerating charges radiate. The total power P radiated by a charge Q with acceleration A is given by P equals to c zeta a to the power n, where c is a dimensionless numerical constant which is equal to 1 by 6 pi. Zeta is a physical constant that is a function only of the charge, the speed of light, and the permittivity of free space, and n is a dimensionless constant. Find zeta and n. So this is a simple dimensional analysis question, and we can work this out as follows. In part B, we can say that P equals to c zeta a to the power n, and so we can also write it as c times the charge. The dimensions of the charge are coulomb. I'll write it in terms of, and this is dimensionless, so this, let's ignore that. Let's assume this is to the power a multiplied by the speed of light, which has dimensions of lt minus 1 to the power b multiplied by epsilon naught which has the dimensions of L to the power minus 3 t square m to the power minus 1 and c to the power 2, where c is the coulomb, and to the power c, multiplied by acceleration, which is Lt to the power minus 2 to the power n, and this must equal to the dimensions of the power, which are m L2 t minus 3 to the power 1. So on calculating this, you can get the answer very easily, and so I'm just writing the end expression which we get for the power. We get power as 1 by 6 pi times q square by c cube epsilon naught multiplied by a square. You can work out the calculations, they are pretty simple, so I'm just skipping them. Now comes the most important parts of the questions. Now consider the electron in first part, except now take into account the radiation. Assume that the orbit remains circular and the orbital radius changes by an amount delta r, which is very less than r. Consider a circular orbit for the electron where small r is less than capital R. Determine the change in the orbital radius during one orbit in terms of the given quantities. Be very specific about the sign. So, and in the other case, we have to work out in the case of when r is greater than r. These two are the cases. So yeah, let's see. So first of all, what we can get here is that the energy lost delta E will be equals to P times time period, and here this is, let's say, for part 1, the time period, and this is with a negative sign because the energy is being lost. And we can also write this equal to the change in total energy, which is delta K plus delta U. Now du by dr can also be written as minus F, which is equals to EQ time over 4 pi epsilon naught times R over R cube. This is applicable for when small r is less than capital R. And similarly, dk over dr can be written as d by dr of half mv square, can also be written as half of d by dr of r times mv square by r. This can be written as the force, and here what we get finally is half of d by dr times r times f, and f, as we know, this is f. So substituting f and differentiating, we get this as eq over 4 pi epsilon naught times r by capital R cube. So from here what we get is minus p into t over delta r is equals to 2 times eq over 4 pi epsilon naught into small r over capital R cube. So from here what we get is delta r equals to minus of power radiated. Power radiated will be 1 by 6 pi times a square e square over c cube epsilon naught multiplied by the time period, which we found out in the first part to be 2 pi root of 4 pi epsilon naught mr cube by eq multiplied by 4 pi epsilon naught capital R cube over 2 EQR. Now again substituting the value for acceleration here, and we can get the final answer as delta R equals to 1 by 6 root of e to the power 5q over 4 pi epsilon naught cube r into mc square to the power 3 multiplied by small r over capital R. So this will be the change in radius, and yeah, there will be negative sign. So this is the main gist. So this is the main format which is very common and which is used in many this kind of problems. So it's better if you do try this in two three times, or in 2-3 different problems. It would help a lot. So similarly, again, working out in part 2 of this part, we get du by dr to be minus f again, and this comes out to be eq by 4 pi epsilon naught multiplied by 1 over r square. And similarly, dk by dr equals to 1 by 2 times d by dr times r times f, just a similar derivation as the previous part. But here we'll have to observe that dk by dr will come out to be negative eq by 8 pi epsilon naught multiplied by 1 over r square. So this implies that as r increases, the kinetic energy is actually decreasing, which is very counterintuitive to such as to think about it. But yeah, that's how it works. And again, working out the similar calculations, we get de by dr as the sum of these two, which is equals to half of eq by 4 pi epsilon naught multiplied by small r over capital R cube, which equals minus p times time period, where p is the power radiated and t is the time period. And working out just as similarly as the last part, we get the delta r to be equals to minus 2 by 3 root of e to the power 5q over 4 pi epsilon naught cubed multiplied by r into mc square whole cubed. So yeah, these are the two major answers. So this is a very typical format of this type of question. So you should try such problems. And there's one more such problem came in this year's IOQP or INPHO equivalent, question number 3. I'll put the link to that also in the description. Be sure to try that also, because that is also very similar. And yeah, thank you.